mine on? Great. All right, let's begin. Happy Friday, everyone. You look more energetic than I had expected, but that may just be delirium. But either way, let's see what we can do with it. So today, the main topic will be 23, and homework help 3:30 to 4:30 in the dining hall, 6:30 to 7:30 in the botany lab. I forgot to mention that there's a play happening, which some folks in this room are heavily involved in, have sort of given their life over to the last couple of weeks. And so that's 7 tonight and then 2 and 7 tomorrow. Is that?
Criterion, and it's free.
Yep.
And it's a common.
Yep.
And if you can't make it, like me, it is being recorded.
Okay.
I don't know when that will.
That's on
Yeah. Let's see. So then next week, 20.4, 20.5, and then we'll do some concluding stuff on Friday. We've covered a ton of material, so I do want to do some sort of retrospective. And 20.5 is also sort of a summary chapter. And then there'll be a final homework due next week, probably a little bit longer than the one this week. This week, I think was short. Okay. So I don't think it won't be a long, super difficult one, but I don't think it's going to be. It might not be as short as this week, but it still shouldn't be it won't be an unusually difficult one so far as I know. All right. So let me say a little bit more about cross products. So cross products, they're a way of combining vectors, multiplying vectors. So the way we've been working with most of the time is dot products, and those are sort of nice because you get a scalar out, and the algebraic formula is not so bad. Cross products are a little trickier, or I guess maybe just a little messier. It's a vector product. The answer is a vector, and so there's sort of two ways of thinking about this. There's a geometric way and a algebraic way. So you take the magnitudes of the two vectors, and that sort of makes sense. So you're multiplying vectors. You're going to multiply their magnitudes together. But then we need to account for the directionality of them. And in this case, for cross products, we do this sort of funny thing where, so we take sine theta. That accounts for some of the direction. But then the answer is a vector, and the direction of the vector is given by the right-hand rule. So it will be in the direction perpendicular to both A and B. So A and B make a plane. And then is it up or is it down? Yeah.
Is up positive and down negative?
Uh,
I'm confused by that M term.
so
I get how we find this, but I don't get how we write it.
how you write it would depend on the coordinate systems you were working in. I mean, so you may, so often, like if they're on a sheet of paper, you might want to say out of the page or into the page.
Okay.
That's probably the easiest way to say it. Or if you're sort of established a coordinate system, x, y, z, then you say, okay, I'm going to take this to be my positive z, and then you can do the right-hand rule and see if you get down or up, in which case it would be negative or positive. So signs for cross products can be definitely a little bit of a headache. Let's see. So the algebraic form is this funny equation, which is most easily remembered as the determinant of a 3x3 matrix. I'm guessing even if you haven't seen matrices before, there's at least a pattern to this. So you're doing I times this minus j, that minus this, plus k, this minus this. So you kind of go across the top, alternating signs, and then it's the diagonals minus the off diagonals. I don't think we're going to have to use this formula much. I'm sort of trying to avoid it, but it's also important that you see it so you know how to generalize this stuff into 3 dimensions. Let's see. So let me say one more thing before you do a warm-up problem. Cross products come up all the time when you're doing the physics of rotations. And a way I sort of think about that is, so what's going on if you've got if you're trying to describe a rotation? Well, you need to sort of, you've got a plane in which the thing is rotating, and the magnitude here might give you this, like the speed of the rotation, the strength of the torque. But then you also need to say, what axis is it rotating around? And that direction sort of typically gives you the axis of rotation. So, so cross products are sort of a natural way of sort of doing the accounting you need to do when you're describing things in physics that are rotating, fluids or mechanics or things like that. So torque, angular momentum, angular speed are all defined in terms of cross products. OK, so let's do sort of a warm-up example numbered 0 on this sheet. And then I'm going to talk about curl for a while, and then we can do the rest of the problems. Let's talk through this. So here is the scenario, an A of 3, B of 2, 2. So here's the picture. The angle is 45. That's a lovely angle. And so we can do this two ways. Let's first use the geometric definition. Magnitude of A, magnitude of B, times sine 45 times, OK, now I have to think and twist our arms and shoulders. So a couple ways to think about this. If you put your index finger in the direction of 3, your other finger is in that direction. My thumb is out of the board. So this would be out of the board. If you were crossing A into B, my thumb is out of the board. We are unscrewing an Algene bottle, and the lid would be moving towards me because I'd be unscrewing it. Maybe I'm the only person who likes to think that way. Anyway, I don't know. Anyway, but all of those ways should give you that it's out of the board. And I would definitely, to go back to Jeremiah's question, I think this is a much better way to think of it. It's the same thing like in physics. Is it like an angle of minus 30 or plus 30? Is it an angle of 110 or is it an angle of 20? I always think like just draw a picture and say like it's this angle. Like here it's like it's out of the board. So I sort of tend to try to think physically about minus signs rather than trying to remember sort of arbitrary minus sign conventions. OK, so this is a geometric picture. We can also use the algebra. It's this big long formula. But since I know that the z components here are 0, that I'm going to get zeros for the I and j term. I'm just going to have the k term, which is blah minus blah. And plugging in, I'm going to get 6, which is the same answer I get the other way, so that's exciting. Yeah?
So when it goes into the board, is negative? You would put a negative sign?
Yeah, assuming you had chosen a right-hand sort of set of coordinate system axes. But yeah, so this would be so when you draw a plane like this and you get to, then you say, OK, well, where's my z-axis going to be? And well, you could say I want positive z to be out of the board or positive z to be into the board. And if normally the convention is to choose a right-hand axis system, which would mean that I would need to choose z to be out of the board, and then out of the board would be positive and into the board would be negative.
So is it arbitrary? Like, because then you would get...
So the convention, the standard convention is to, whenever you have like three-dimensional coordinate systems, to choose a right-handed coordinate system. I mean, you don't have to, but that's sort of the normal thing to do. Likewise, cross products, torques, everything are defined so that right-hand rotations are positive. But there's no, that's just an arbitrary thing. It's not any law of physics. It's just like we decided we're going to do it that way. Like who decided that right is usually positive? I don't know. Yep. Right, yeah, so you have to be consistent. That's the main thing, yep. So like where might something like this arise? This is just sort of a little physics aside. Torque is R cross F. So suppose you're trying to rotate, like open the door, and you push on the door this way. So torque is like turning force, or tendency to make something turn. And so, well, you need, the best way to open a door is to push perpendicular to the door, right? Like if I wanted to rotate this, I would push it this way. I wouldn't, probably be less efficient to push it that way, but at least it would work. If I pushed it horizontally, it wouldn't rotate at all. And of course, the harder you push, the more the door is going to turn. And you want to push out at the end of the door, not in the middle of the door, for maximum torque. So this cross product sort of like does the accounting, accounts for all of those little bits of physics that I just said. And then like which way is this going to turn? Well, again, that depends on your orientation, the orientation between F and R. And if you did it this way, you can see that it's going to turn in this direction, which again would be a positive rotation. So I mean, I think we're not going to do any more mechanics. This was a like little 3-minute foray into mechanics. But when I said like cross products are just the total natural vector way to account for rotations, that's what I was sort of getting at. So. Oh yes, thank you. I was so excited that the that those canceled out. Yeah. So okay.
Wait, Dave, are we ever going to get cross products that have other than k values?
So in life, yes. In this class, probably not.
But what would that mean? Like, because I get how that's 6. Like, that 6 makes sense to me. And, like, I understand what that 6 is saying. But I wouldn't understand if it was, like, 2i plus 5j plus 6k. That would confuse me a lot.
All right. So, oh boy. So, like, if we... I mean, so just geometrically, if any two vectors define a plane, it's probably going to be, I'm probably just going to give up on drawing and just start doing this. So these two vectors define a plane. And then I could cross one vector into another. And then the direction of the cross product is perpendicular to this plane, so it would either be this way or that way.
Okay.
Yep.
Yep.
Okay, so now let's do the thing you've all been waiting for, which is the dot product gave us one type of vector field derivative. The cross product's going to give us a different type of vector field derivative. So let me introduce this type of vector field derivative first geometrically and then algebraically, and then we'll spend a while doing a series of hopefully fairly simple calculations to sort of get a geometric feel for this. Okay, so maybe I'll recall that we had flux density was a limit as v goes to 0 of S f dot dA over v. So at a given point in space, we imagine putting a little sphere or a cube around it and asking how much flux, how many butterflies or electric field lines are flowing out through the surface. And then we let that surface shrink down, and that gives us the flux density at that point. And make sure that I use the same notation as the book. By the way, has anybody seen my calculus book? I couldn't find it in my office, so I assumed it was at home, and then I couldn't find it at home, so I assumed it was in my office. And now I'm sort of stuck in a loop of assumptions that seem to not be borne out by fact. So anyway, so I'm using one future edition of the book, which is nice. It's in good shape, but I'm a little like to find my old book. So we can then also similarly define the circulation density, CRC. guess I'll write this out. So flux density, and then we have circulation density. So recall that circulation is the line integral around a closed loop. So you kind of go around in a path and you say, was the field on average, was the net effect of this field, was it to do nothing? Was it in my face and coming at me? Was it at my back? And so at a point in space, we can say, what is the circulation density? So this is, think maybe a three-dimensional fluid. We choose a point in space, but we also then have to choose a direction. I want to know, is there rotation in this direction? And that, when you specify that rotation, that's specifying the vector that's perpendicular to the direction of the loop you're interested in. And this is the area inside C.
Basically, you're calculating the vector coming out of an area.
So you're calculating
What component of the circulation is going that direction?
I guess you could. I would sort of invert that sentence, and I would say, you're choosing in this setup, you're choosing a direction, and then you're saying, what's the circulation around that axis?
Okay.
So you choose a point in space. So we've got some crazy flowing fluid. You pick a point in space, you pick an orientation, and we can figure out the circulation.
Around the point.
Around that point, yep. So like, here's a point in space, and then maybe you want to know about the circulation in this direction, so then I would do a loop in this direction. If somebody else wants to know the circulation in this direction, I would do a loop in that direction. Yeah.
So it's like you're putting a net in a direction and measurement will go through.
No, it is like, sorry, and that long drawn out no was sadness directed towards myself, because I actually because I made, okay, so imagine I made a little thing that I then forgot to bring to class. I'll bring it next time. So imagine instead of a net, so nets are like are catching butterflies, and that's what flux is about. How many butterflies are flowing through a net or a closed net? This is there sort of like, I think of this as like local whirlpoolness or local spinniness. And so how would you test that? So imagine, oh gosh, and so since I didn't bring this little thing in, I'm now going to have to try to draw it. Imagine putting a little paddle wheel in. So and let's see, so like, so the idea is, like, you'll have a stick and then like a little paddle wheel, and then you put it in, and it could rotate. And so if you put this in a whirlpool, like when the water's draining out of a sink, it starts to spin around. And so if you put this little paddle thing inside that whirlpool, it would spin in the direction of the whirlpool. Whereas if you just had like a stream that was flowing in a straight, uniform way, and you put this thing in there, it wouldn't spin, because you'll have the same force on both sides, it would just balance out. So this is sort of like a spinniness probe. So rather than asking the amount of stuff that's flowing through the surface, I'm asking, is there a little whirlpool in that orientation? Yeah.
Are you trying to have your integral convert to 0, or like reach a limit, or are you just like, can you have like a huge area?
So I guess if I'm wanting to do density, I should have that. Yeah.
Okay.
Yeah. So just like we want the volume to go to 0 so that the flux density is constant at that point here, we're going to let the area go to 0 so that the circulation density is constant at that point. All right. Let me let's see. Let me write down a few more definitions, and then we'll start calculating the stuff, and it'll become more concrete. All right. So, okay. So flux density is also called the divergence of a vector field. Circulation density is also called the curl of a vector field. And okay, so the curl is a vector field. So in order to specify a vector, I need to tell you two things geometrically. I need to tell you the direction and the magnitude. So the direction of the curl is the direction in which the circulation is the greatest. And then the magnitude of the curl is the circulation density in that direction. So let me let people a second to write, and then I'll say a little bit more. So for the circulation density, you get a different answer depending on what n you choose. You're at a point in space, and you want to say, is there a whirlpool? And it's like, well, whirlpools have an orientation. You need to choose an orientation, and then this will tell you how much of a whirlpool you have. And different orientations give you different whirlpooliness. So then the idea is, well, let's choose the direction that gives the greatest whirlpooliness, or the greatest circulation. That's what this is. And then what is that whirlpooliness or circulation in that orientation? That's going to be the magnitude of this vector field curl. So that's the aesthetically pleasing vector notation for this. And this is going to give us an algebraic definition of curl. And here we go. So we're going to have I, j, k, partial x, partial y, partial z, f1, f2, f3, and then we take the determinant of that. It may or may not be worth writing all of this down, but at this point, so this is going to be partial f3 partial y minus partial f2 partial z in the I direction minus partial f3 partial x minus partial f1 partial z j plus partial f2 partial x minus partial f1 partial y j k. So it's not awful, but it is a little bit of a mess. All right. So at this point, I think we should start calculating this, just working through some examples. These are, I hope I tried to have these be pretty simple examples that will illustrate some features of curl. So let's try stepping through 1, 2, 3, 4, 5, 6, maybe. So we'll spend the rest of the day just kind of working through these examples, and we'll see what you think. That wasn't an option. I don't have any more stories right now. If I think of any, I'll let you know. OK, so let's talk through this. We are recording. Great. OK. So all right. So for this one, it's 0 because there's no, as you're stepping along this path, it's never helping or hindering you. It's always perpendicular to you. Here you can see, all right, we're going to get a pretty big negative contribution, because the field, it's this whirlpool thing, and you're going against the flow. So it's always going in the opposite direction that you're going. So there's sort of two ways to think about this. And let's start with algebraic, since that's kind of what we're in the thick of right now. Like, oh, great, a circle. We have to parameterize a circle. Well, it could be worse. We remember how to do that from 2-3 weeks ago or something. So then here's R. This is the vector, parameterized vector from 0 to 2 pi that describes that circle. We need to take its derivative. There's that. When I was doing this before, I kept putting a b here. I don't know why. So then we need to do f dot dr. dr is r prime dt. T goes from 0 to 2 pi. For this f, I need to plug in the values of the field along the path that I'm walking. So I need to plug in this for x, this for y. Doing so gives me this. And now, here, nice things start to happen. Now we can actually do the dot product. I'm going to get a minus a squared sine squared. And I'm going to get a minus a squared cosine t squared dt 0 to 2 pi. Sine squared plus cosine squared is 1. That's the one trig identity number. And then this is exciting because we're integrating a constant, and we like integrating constants because we can pull them outside the integral, and then this is just going to be minus 2 pi a squared. Yeah.
Can you do the same thing without doing the parameterization? Just do that.
Yeah, so you can also say, you can say, hey, wait a minute. This field has a constant value. The field is always right in my face. And the field always has a value of A. Great, because the value of the field here is A, here is A, here is A, here is A. And so then this path has a length of 2 pi A. So you're experiencing A in your face for an entire journey along the circumference of 2 pi A. So that's going to be A times 2 pi A, which is 2 pi A squared. However, half of physics is physics with a minus sign. Oh, wait, it's in my face. not at my back, we define that to be negative. Is that what you meant?
No.
Sorry. Hopefully that was good anyway. But
I meant if we can use this scalar curl.
Oh.
In both cases. Like
Yep.
I did that.
Yeah, that'll be.
And I don't know if it was a case that it worked in both ways. Like what
It will work, and so.
Okay, which is way easier than dealing with cosine and sine.
Yeah, exactly. Yep. And that was how we were going to end class. With that, hey, there's an easier way to do this, but you've discovered that already. But that's okay. That's totally okay. So Margarita was reminding us that we know a better way, or a way that's often an easier way to evaluate this, which is to use the scalar curl to convert this into an area integral. And so I'll mention that at the end of class, and that'll sort of be the focus, actually, of class on Tuesday. Okay. So, okay. All right. So let's carry on and do these two, and then we'll talk, kind of come up for air and talk about what this means geometrically. So let's look at f first, and then we'll talk about g. Okay, so f is a pretty boring vector field. It's constant. Will you experience net circulation along the orange path? No. No. So along here it's 0. Along here it's 0 because it's perpendicular. Here it's at your back. Here it's in your face. But those cancel out. So you would get a plus, if I did it right, a plus 2s this way, a minus 2s this way. The field is 2. Here it's helping you along for a distance of s. Here it is hindering you for a distance of s. So it gives you a boost of 2s, a hindrance of 2s, for a total net of 0. OK, so let's take a look at g. So now, and you can sort of see this from the drawing. The field is different in different locations. So if OK, and this side is s. So when I'm up here, I'm at s. My altitude, my y, is s over 2. So then I'm plugging in s over 2 here, and that gives me this. So it's so we don't have to really do the integral. Well, we do the integral, but we're integrating a constant, which we like, because then you just take the constant and multiply it by the length of the integral. So this s is because this path has a length of s. Down here, I'm now plugging in for y. Y is minus s over 2. It used to be plus. Now it's minus. The path has a length of s, and this is because I'm moving in the opposite direction. And so if I add those together, with this minus, these terms cancel, and I'm going to get s over 2 plus s over 2, that's s, times s is s squared. Yes?
I was super confused by this problem because I don't get how, I feel like the top should be bigger than the bottom one because the equation then moved up one. So I don't know. I'm just confused. I guess that's how we're getting the s squared. Never mind. That didn't make any sense, but it made sense in my head a little bit.
I mean, the top. So.
Well, I just don't get how, it's the negative, or s over 2, and I don't know, I just feel like it's somehow, I don't know. I'm confused on the whole integration that you did.
So this gets larger as y gets, ignoring the minus sign for a second, this gets larger as y gets larger. And so that's sort of what's going on, right? Is that here you've got this field that has now different strengths for different y values. So that's why they're not going to come to 0. So that's sort of like the kind of basic sort of physical picture. If I were to write this out, and I'm sort of being a little bit careless and physicsy with minus signs. But one can see that this is going to give a net. Well, OK, so let's think about why this might be positive. So this is going to, there's going to be a net. If I were to put this little whirlpool meter in here, it would be spinning this way, which by the right-hand rule is out of the out of the board, which by the normal convention would be positive. So the fact that we're getting a positive number here, I claim makes sense. The fact that we're getting a negative number here, what type of whirlpooliness is it? It's this type of whirlpooliness that would be in the board, which would be negative, which is why we get a negative. So let me go ahead, if I can. Well, actually, have people done number 5 yet? OK, so let's take a couple of minutes to look at 4 and 5. So now we're going to calculate the curl of this field using this big equation, which really is just going to boil down to this. And hopefully that will lead to a pleasing conclusion for the class. So let's talk through these. So first, here I'm coming up with a circulation density. So we found circulation, but to get the density, I want to divide that by the area of the thing I found the circulation around. So here we found a circulation of minus 2 pi a squared. I want to divide that by the area of the circle, and I end up with a circulation density of minus 2. You think of that like as a whirlpooliness, twistiness, or a curl. This one's 0 for g, the one we were just talking about. We have an s squared. The area of the square is s squared. That gives me a whirlpooliness of plus 1. OK, so that's sort of thinking about this geometrically whirlpooly stuff. Here, this is just calculus algebra magic. And again, since f3 is 0 for all of these, none of these vector fields are up or down, that's going to, and there's no z sort of variable here. That's going to get rid of both the I and the j terms. We just have to worry about the k term. So if I calculate the curl of b, so that's the x derivative of f2 and the y derivative of f1, lo and behold, that gives me minus 2, which is exactly what we calculated using the geometric method. Here, if I calculate the curl for g, there's only an f1 to contend with, and f1 only depends on y. It doesn't depend on z or 3, 2. Doesn't depend on z. So there's a minus here from the formula. There's a minus from the field. The derivative of y is 1. Minus minus is plus. Plus 1, just like we had before. Yes?
If we're looking for the integral we were looking for before, is it fine to just multiply the curl by the area and then get the integral?
If the curl is constant.
OK, if it's not constant.
If it's not constant, then you'll have to do an integral. So let me let's see. So two things I want to do to conclude. First is, so these are 4 vector fields, and we now know about 2, and there are really only 2 ways of taking derivatives of vector fields: divergence and the curl. or at least two sort of primary ways. This field has a curl of 0. It's not whirlpooly or cyclonic or solenoidal or twisty at all. It's a pointy. E, so the divergence of E is 2. A lot of butterflies are hatching here. Or there's a positive charge that's making field lines go out. This isn't, I called this E because this is electric field-like, but it's not actually electric field-like, because if it was electric field-like, the lines would be getting smaller rather than larger. But then you'll have a 1 over r squared, which nobody would want to deal with. So this should be like E in quotes or something. B, this is a field that's all whirlpooly and no divergence at all. There are no butterflies being created. The butterflies are just going in a circle for eternity. There's no water that's getting created. It's just spiraling around. This field is a constant. It doesn't change at all with respect to x or y in any direction, in any component. So both of its derivatives are 0. It would be shocking if a constant field had non-zero derivatives. And then this is another example of a curly or twisty field, because you'll have some rotation this way, but you won't have any divergence. You might have a lot of butterflies on this altitude, and then not so many here, and then small numbers of butterflies in this direction. But there are no butterflies that are hatching in this scenario. There's just an infinite stream of them, and we won't ask where the butterflies came from. That's cosmology. Okay, so that's sort of like differential calculus for vector fields. And then let me just mention the result that we'll talk a bunch more about on Tuesday, but which some of you have already sort of anticipated, which is that suppose we have something like this. We can replace it with this. So this is what Margarita was mentioning earlier and what Jeremiah just mentioned. And this is known as Stokes Theorem. And this is another fundamental theorem of calculus. It takes an area integral and replaces it with a statement along the boundary. So this tells us if we have an annoying circulation integral to do, if we calculate the curl of the field, maybe we get lucky and the curl's constant, and then it's a super easy integral to do. So we will do a little bit more with curl, because like a lot happened towards the end of class. Maybe we'll do a few more examples, and then we'll explore the consequences of this relationship as well on Tuesday. So I'll be in the lecture in the dining hall for a little bit if people have questions.